Hello, everyone. Welcome to today's show. Our guest for today is an internationally renowned physicist, Professor Keith Riles. He's a member of the LIGO scientific collaboration, which in September 2015 discovered gravitational waves from the merger of two massive black holes. He carries out research into the fundamental forces of nature, working in both gravitational and elementary particle physics. We welcome you, sir. So our very first question from you is, how was your childhood, your school life, and how did you exactly get into the field of physics?
Okay. Well, my childhood was split between New Orleans, Louisiana, and Redondo Beach, California. So we moved from Louisiana to California when I was about 13. So my early years were in the largely in the French Quarter in New Orleans. It's a historical district, and I went to a variety of different schools. I went to private school for a few years, and then to Catholic school for a few years, to public school for a couple of years, and those experiences were different in many different ways. During part of that schooling, I did get some exposure to science, not a lot, but it did pique my interest a bit. And then when we moved to California, I went to a public school, public middle school, and then public high school. And I really didn't get much science in that part of my education. I would not say I went to very strong schools in California.
Okay.
And this all happened in the 1970s in the era of the Watergate scandal. And journalism was a very hot, glamorous career at that time. So I was planning to be a journalist, and I worked for the school newspaper in high school. And up until my senior year in high school, that was my career plan. I was going to be a journalist, and I was going to be a novelist, and you know.
Wow.
But then I was required to take physics in my senior year, and I didn't have any particular interest in physics. I had a mild interest in it, but I would say within the first week of just reading the first chapter of the physics textbook, I started thinking, this is pretty interesting. And the more I got into it, the more fascinating I found it, because it really answered all sorts of questions I had about everyday physical phenomena. And I just, it opened up a whole new world. So my career plan shifted dramatically during my senior year in high school. And then I went into college and just pursued physics from then on. I still had an interest in writing. I still took English courses and such, and I still had some aspirations to do some writing. But in the end, I mostly did physics.
Oh, that's something very interesting. Someone who wants to become a journalist and then coming into the field of physics. It's interesting. So this must have helped you in writing the research papers, right? The research papers that you write, the English must have helped you over there.
I suppose so. I don't enjoy that kind of writing, but I can do it.
So what kind of writing you enjoy otherwise?
Oh, I would enjoy writing fiction or essays. I don't do very much of that sort of thing at all, but that's more enjoyable. I do actually enjoy writing articles that are somewhat pedagogical, review articles and articles that try to teach how things work. But the more technical articles that we write as part of a research, those are difficult to write because you have to get everything exactly right, and it's so easy to be less precise than you'd like to be. So it can be a bit grueling to go through to write a technical article.
Okay, so we will move on to the next question. The second question I have for you is, how did you enter the discipline of gravitational physics?
Well, I started off my career in particle physics, and I worked for many years at high energy colliders. I did my graduate work at the Stanford Linear Accelerator Center in California, and then as a postdoc, I moved to the CERN laboratory in Geneva, Switzerland. And then when I moved to Michigan as a faculty member, University of Michigan, I continued uh, carrying out research at CERN, and I was going back and forth across the Atlantic for many years, and I enjoyed that. I worked at the what was known as the LEP Collider, Large Electron Project Collider at CERN. Um, but in 2000, that was shut down to make way for the magnets that would become the steering magnets for the Large Hadron Collider. So the LEP Collider was replaced, literally replaced in that tunnel by the Large Hadron Collider. And I didn't have as much interest in pursuing um, the experiments that were going to be done at the Large Hadron Collider. I found it somewhat interesting, but I also was more interested in learning something new, and
Okay.
I had the opportunity to work on the LIGO 40-meter prototype instrument at Caltech back in 1998, and I decided that my very first sabbatical as a faculty member um, would be to try out gravitational wave physics, um, working at that interferometer, and I did that, and I just loved it. I really fell in love with the science you can do with the interferometers. I like the interferometer technology. It was very different from what I'd worked on as an experimentalist in high energy colliders, building detectors. So I enjoyed that very much, and I decided that this is a really exciting new field. I did not appreciate at the time how long it was going to take us to make the first detection. If I had appreciated back in 1998 that we'd have to wait until 2015 to get the first detection, I'm not sure I would have stuck with it. But fortunately, I didn't know that, so I kept plugging away at it.
So it turned out well then.
It did eventually, yeah.
Okay, so we'll move on to the next question. Uh, the next question is, tell us something about your work on gravitational waves and where it fits into the present findings.
Okay, so I've worked in a variety of different areas, primarily in data analysis since I began working. I initially worked in what's known as detector characterization in trying to understand some of the artifacts in the data. I spent a great deal of my time in the initial LIGO days in the 2000s working in that area and helping lead a team of other scientists working in that area. Um, but around, well, I guess in the mid 2000s, I started spending more of my time um, trying to determine the best way to detect continuous gravitational waves. So those are gravitational waves that might come from a spinning neutron star in our own galaxy. So instead of looking for a source that is hundreds of megaparsecs away, in principle, there are some sources right here in our own galaxy, uh, hundreds or thousands of parsecs away, that we could detect in principle. And these are um, slightly deformed, non-axisymmetric neutron stars. So neutron stars are these stars that are very compact, almost black holes, but not quite that compact, that have radii somewhere in the ballpark of 10 to 12 kilometers. And we think they're very smooth. They're made up of neutrons, and we're not sure exactly what's inside of a neutron star, but one reasonable guess is they're mostly neutrons. Um, but there could be a little bit of an asymmetry. These are about as smooth as a billiard ball, but much larger. And you can imagine that the crust of a neutron star, which is thought to be rigid, could have
Yes.
cracks in it. There are
Mm-hmm.
strong magnetic fields in the
Mm-hmm.
vicinity of a neutron star. So there are reasons to think that a neutron star is not quite perfectly smooth. And if it has a bit of a bulge on its surface, sometimes that's called a mountain, but I think a bulge is a better way to think about it. Um, then as it spins very rapidly, um, it will tend to swirl the space around it, creating gravitational waves. So the warping of space is perturbed by this bulge that's going around and around. And these things can spin fast. The fastest known neutron star spins at 716 times per second. So that's the size of a small city spinning around 700 times per second. Um, so it doesn't take much of a deformation on the surface of that star to stir up space a little bit. And if that were to be the case, then we could look for a nearly monochromatic, that is to say, a nearly single frequency signal in our gravitational wave data channel. Um, Now, there are quite a number of challenges associated with that, in large part because the Earth is moving. The Earth spins around its axis once a day, so the detectors are moving at about 1 part in a million of the speed of light, 10⁻⁶ of the speed of light, which doesn't sound like much, but it's actually significant. And more important, the Earth is going around the sun at roughly 10⁻⁴, 1 in 10,000 of the speed of light. And that means that the frequency at which we detect the gravitational waves is constantly modulated by Doppler effects. So I think most people are familiar with Doppler effects from sound. You know, an ambulance coming toward you or away from you has a slightly different pitch to it. And the analogy to that in gravitational waves is such that you would see a slight variation in the frequency of the wave. And so what would you would normally think of as being a monochromatic signal from this almost constantly spinning neutron star actually is not all that monochromatic when you look at it in the rest frame of our moving detectors. And it seems like a very small effect. I mean, why would 1 part in 10⁴ be important? But it actually is extremely important when you try to look for the signals that we think are as weak as they are. We think that they are, well, we have very good reason to think that those signals are weaker than the signals we've detected from neutron star mergers and black hole mergers by about a factor of 100,000 or more. They are incredibly weak. And the only chance that we have to see them is by integrating our data over a very long period of time. So we don't just look for a sudden change, we're looking for a continuous signal that's there for an entire year. And we can exploit that to dig into the noise of the data to pull out the signals. Now, so far we've not yet found one, but we're continuing to hunt. Every time we get a new data set, we look again, and even with our old data sets, we try to dig deeper in the noise using special techniques. So I spend a lot of my time thinking about how to do that better and working with my students and postdocs to carry out those searches.
That's awesome, sir. Okay, sir. So the very next question we have for you is: you were a member of the LIGO scientific collaboration, which in September 2015 discovered gravitational waves from the merger of two massive black holes. How was that feeling?
Oh, well, it was fantastic. I do remember, the the moment when I first realized that that the merger was real. Um, you may not, I don't know if you're familiar with the history of this, but we were in nominally an engineering run at the time. We hadn't even officially begun our first observing run. We were in the kind of the warm-up stage of making sure that everything was working properly, and not everything was quite ready to go in terms of software and hardware. But nature didn't wait, so we got the signal, and I remember reading this email over breakfast that morning. Someone said, "Yeah, there's an interesting event here," and there was some question about how good the data quality was, and so on. And so when I went into the office, I started looking at the data, and I could see that, yeah, this is a remarkably intense signal. It must be a hardware injection. Yeah, that was my initial thought, because we never seen anything remotely this strong
Absolutely.
before. Um, and we had this infrastructure that was set up to allow us to simulate signals in the interferometer by literally pushing on the mirrors. There are various ways of doing that, but um, I was familiar with that system because I myself worked on the continuous waves simulations in hardware injection. So in fact, I'd been working on hardware injection machinery just a few days beforehand to make sure that the continuous wave injections would work correctly. And the thing that puzzled me was that I knew that we weren't quite ready. Um,
Okay.
I knew that we were waiting for some calibration curves to come from the calibration team, and they'd given us something preliminary, but I knew it wasn't quite good enough to do accurate simulations. So I was waiting myself that week to get those updated functions so that I could update my own injection infrastructure. And so when I saw that injection, I thought, wow, someone was really brave to try and pull that off when we know that we're not quite ready with our calibration functions. Um, and the other surprising thing was I knew that this was not um, a standard hardware injection because I was part of the injection team and no one had said they were going to do an injection like this. So I thought, okay, well, this must be the blind injection team because there was a secret group
Okay.
who were authorized to put secret injections into the data to test the rest of us, to make sure that we could actually detect something that had been planted without knowing ahead of time, when it would occur. And so that team existed. We knew they were planning to do an injection at some point. But again, I was really surprised. Why would they do it so early? Because we know we're not ready to do these kinds of tests. And they were supposed to tell us when they were going to do their testing, even if they weren't going to tell us when they were going to do the actual injection later on. So the whole thing was very, very puzzling. And then I attended a teleconference at noon that day, the detector characterization teleconference, where I hoped to understand better what was going on. I assumed someone was going to say, "Yeah, we went ahead and did this hardware injection just to test things out." But almost at the beginning of the meeting, someone said, "No, this was not a hardware injection." And I just sat back in my chair because I realized, oh my God, this is real. This is the real thing. Um, and so yeah, in some sense, my world changed from that day on.
Wow. Could that injection have could it go possibly wrong in some way if if you thought that we were not that ready at that time? Uh, was there a possibility that it could go wrong also in some sense?
Well, yeah, if there had been an injection, then um, it could easily have been highly distorted. Probably, in fact, I'm sure it would have been. As I said, we did not have the right software tools in place at that moment. We did later in the run, and we would have had them later on that week, except that once we saw the detection, everything was frozen. We were no longer allowed to touch anything in the way of software, particularly injection software. So we had to wait some number of weeks before we had the opportunity to put in the correct actuation functions for the injections. So had someone tried to do an injection, it probably would not have looked realistic at all. It would have had all kinds of artifacts in it.
Okay, so someone's curiosity led to this discovery.
Well, the whole collaboration was ready. Yeah, there were some aspects of the system that were not ready. As I mentioned, the injection system itself wasn't quite ready. Um, but the calibration team had done a nice job of actually calibrating the interferometer. They'd done some work just the previous couple of days, and the um, the analysts who were analyzing the data more or less in real time as it came rolling off a detector, they were ready. Their software was ready to go, and in fact, it was one of those programs called the Coherent Wave Burst program that first told us that something had happened, and it worked beautifully. It did exactly what it was supposed to do.
Great. Our very next question is gravitational waves are extremely small and short lived. In fact, for the first detection, scientists had to measure a distant change 1,000 times smaller than the width of a proton. How do you measure such disturbances?
Okay, well, there are two important uh, issues to keep in mind. I mentioned before that a Mach interferometer is a null experiment where you run it in such a mode that most of the time you don't see anything on your photodetector or you see very little light. And if a gravitational wave comes along, it perturbs the destructive interference pattern. And so suddenly light does start appearing on your photodetector. And so you see a modulation of that intensity. That's your signal. Okay. Now, I guess the two key things to realize are first, that we're starting from laser light, which is already short in its wavelength. And second, we're dealing with high intensity lasers, high intensity laser light, I should say. So the wavelength of the laser light that's being used is about 1 micron, about a millionth of a meter. And so in some sense, you can think of that as being a ruler. You can get a little bit, it's a little bit misleading to think of it simply as a ruler for various reasons, but as a first order approximation, you can say, well, that's the ruler that sets a scale, a millionth of a meter. And even with a Michelson interferometer that's been constructed from a cheap laser pointer that you might use in the classroom, you can measure distances of order 10 to the minus 7 meters very easily, a tenth of a micron. And really, you could go down to 10 to the minus 8 meters without too much difficulty, just using an ordinary laser pointer. So you're already in pretty good shape if you're trying to measure distances of the order of 10 to the minus 7 to the minus 8 meters with a small laser. Now, the LIGO lasers are much more powerful than that, and the light is amplified in the arms of the interferometer. So each arm of the interferometer is itself an optical cavity made by two mirrors, one at each end, and the distance between those mirrors is tuned to be roughly a half integer number of wavelengths of the light. And so by tuning it that way, you ensure that the light goes back and forth and constructively interferes with itself. And so as a result of having a pretty good laser to start with, and then having this amplification, and there are actually a couple of different stages of amplification, you have more than 100,000 watts of light in each arm of the interferometer. So that's an enormous amount of light, and more to the point, it's an enormous number of photons, all the quanta of light. And this is where you take advantage of the statistics of large numbers. So you can think of it as in the ballpark of 10 to the 24, more than Avogadro's number of photons going back and forth every second in that arm of the interferometer. And so you're in the realm of large number statistics, numbers of photons. And the statistical fluctuations on 10 to the 24 photons is about the square root of 10 to the 24, which is 10 to the 12. Okay, so that means that the inherent fluctuations are 10 to the 12 photons out of 10 to the 24. So that means that the relative change in the intensity of the light is basically 10 to the 12 divided by 10 to the 24, which is 10 to the minus 12. So it's 1 part in a trillion. So in some sense, you have a precision, an intrinsic precision on the light intensity at the level of 1 part in a trillion. And that's what allows you to look much more precisely at the interference pattern caused by that laser light wavelength of order of 1 micron. And very crudely speaking, you can say that you gain by a factor of a trillion in your precision. And that takes you down from roughly 10 to the minus 6 meters down to 10 to the minus 18 meters. And it's actually a little bit better than that. But the two key points are you're starting with a very short ruler to begin with, laser wavelength of a micron, and then you are exploiting an enormous number of photons with statistical precision at the level of 1 part in a trillion or so. Now that's a gross simplification, but it does capture the essence of how it's done.
Okay, so we have the next question for you. Gravitational waves are a difficult subject to study. What impact does this research have on the lives of ordinary people?
Practical applications of the gravitational wave science itself anytime soon. I think that it's more a matter of just revealing new things about the universe. That stirs up excitement understandably so, um, to be detecting gravitational waves from black holes, um, and to essentially confirm that black holes look like the things that we've thought they might be all these years, um, is really nice. We've confirmed an enormous number of predictions about what would happen when black holes collide, and before we confirmed them, we really didn't know. I mean, these are pretty exotic objects, and we don't really understand what's at the center of a black hole. We just have a an understanding of what happens on the outside of a black hole in this vicinity. Um, so these are truly exotic objects. They, in classical general relativity, they, in some sense, have singularities at their centers. Infinite density, infinite mass. Um, Presumably, that's not actually the case. Presumably, general relativity, Einstein's gravity, has to be modified when you get down to those kinds of distance scales. But we don't know at this point how to do that. Um, these are objects that, in principle, are really pushing the limits of our understanding of the nature of space and time itself. And so it's been gratifying that the predictions of how they look from the outside have been fulfilled. They've been confirmed by our observations to pretty high precision now. And that was not something you could take for granted before these detections. Um, so now we're doing, in some sense, precision black hole physics as we start probing ever more precisely to understand their properties. Um, just the fact that we're now doing science directly with black holes is already pretty interesting, and hopefully that stimulates some excitement in the general public, and I think it has. Um, so I think it affects people in making them aware of how interesting our universe is. Now there could be some practical applications to the technologies. Um, this is this technology of measuring gravitational waves to such incredible precision has involved pushing the limits of the technology in interferometry and optics, quantum technologies, and there may be some practical applications in the future. In some sense, there already are in very specific areas of technology, but it's possible that something could affect an ordinary member of the general public just from the technological spin-offs.
Okay, so the very next question I have for you is, in the next 5 years, where do you see gravitational wave astronomy?
Okay, so it's really hard to make confident predictions. We expect that the interferometers will improve steadily in their sensitivities, which allows us to dig deeper in the noise and thereby see further out into the universe. Now, as we go further out in the universe, we see more and more sources. One thing that's useful to remember is that the volume of space goes like the cube of the radius of, say, a sphere. And so as we improve the radius to which we can see something, and that's really a measure of the inverse sensitivity of our detectors, which are getting lower and lower, um, we gain like the cube of the distance to which we're seeing. And so a relatively small change in how far out we can see can make a significant difference in how many sources we see. It's quite possible that we'll go from the roughly 100 detections we've made so far in the last several years to well over 1,000. It's not even out of the question we might see 10,000 detections in the next 5 years, say. It depends on the progression of technology, how long we take data, and so on. And so, at a very minimum, that's going to give us more insight into the formation of the black holes that we're seeing. We have seen some hints in the distributions of the masses of the black holes that there's some structure there. It's not necessarily just a smooth curve that goes from lots of masses, lots of stars around 10 solar masses or so, and then just dropping off gradually as you go to higher masses. There have been some hints in the data that there might be some bumps where there are enhancements in the population. That's still very controversial at this moment. But if we get 1,000 or 10,000 black holes, we should be able to nail that down, if there really is the kind of structure that we've seen hints of. And if there is, then that starts to give us some insight into how these black holes were formed in the first place, because it's, some of them are quite heavy, much heavier than you might naively have expected. And it'll be interesting to try and sort out how it is that we ended up with such heavy black holes. And then there are also going to be binary neutron star mergers seen. And those are very interesting because unlike the case of black hole mergers, where there's nothing left over except another black hole that is basically invisible shortly after the merger, in the case of binary neutron star mergers like the one we saw in 2017, there is something left over, and it produces all kinds of electromagnetic signatures, X-rays, gamma rays, radio waves, optical, and other astronomers can look for those signals and try to understand what happens in the aftermath of one of these mergers. We have pretty good evidence from the 2017 discovery that many of the heaviest elements in the universe are produced in those kinds of collisions, like gold and uranium, platinum. It could well be that is the dominant source of those very heavy elements. So the more mergers like that we observe, the more we can test our understanding of how that has come about. So that would be using more statistics to improve our understanding of the kinds of detections we've already seen. Now, what's more exciting is possibly seeing new sources. Now, I mentioned earlier that I'm interested in continuous wave sources, basically spinning neutron stars in our own galaxy. Well, we might start seeing those. And for me, that would be very exciting. And that's in part because that's what I work on, and that I'm very keen to see that first signal, but also because once you see it, you can keep studying it. Unlike these transient mergers, which happen and then they're gone, if there's a neutron star that's spinning continuously out there, we can study it for years, decades,
and we'll be able to predict the changes and all. What's exactly happening? We'll be able to find more data and study it more precisely and accurately.
That's right, and we can also collaborate with electromagnetic astronomers who can also try to observe the same neutron star, perhaps in X-rays, perhaps in radio waves, and we can try to correlate the changes they see with the changes that we see in gravitational radiation, and to try to understand what that's telling us about the structure of a neutron star. I mentioned earlier that we don't really understand what's on the inside of a neutron star. We have some models, but we can't do experiments here on the Earth, at least not currently, that allow us to probe the kinds of energies and pressures that are relevant inside of a neutron star, so that we don't really have firm predictions of what to expect there. And the theoretical uncertainties are very, very large. So it's not as if we can just do a calculation on a computer that's going to tell us what's going on. They're just not reliable enough to do that.
It's more of a theory right now.
I'm sorry?
It's more of a theory. It's more theoretical right now.
It's very theoretical at the moment. I mean, it's well grounded in nuclear physics and our understanding of nuclear physics, but it's just that neutron stars are probing a regime that is not accessible to experiment here on the surface of the Earth. It's not the density so much as the sustained pressure, and the effective temperature is actually quite low compared to the characteristic energy scale of these neutrons. That's a technical detail, but basically we don't have anything like that in a laboratory here on the Earth.
Yes, that's interesting, man. Okay, so the next question, probably I heard this from you, but I would like to know more. What other interests do you have besides gravitational wave research? One is for sure the writing thing, I know.
Yeah.
I would like to know more.
Well, I guess another area of science I find it very interesting is evolution. I've always enjoyed reading books about evolution. It's not that I do any science there myself. I'm certainly not a researcher in that area, but I enjoy reading books written by researchers who are trying to understand the evolution of life here on this planet, and evolutionary effects on human beings. There's been quite a bit of evolution in our history, and we have a lot of relatives, so to speak, in the fossil record. And of course, modern apes are pretty closely related to us. So I find all of that fascinating. As I said, I don't do research there. I just like to read about it as a
Oh,
dilettante.
okay. Okay, so the last question I have for you is, what is one piece of advice you would provide to young people who want to pursue careers in science? And especially for people in India with LIGO-India coming up. How do you see that in picture?
Well, I'm looking forward to seeing LIGO-India, come to life. I think that will be very exciting. That's going to give us a much better localization or triangulation of the sources that we see, to have another interferometer on the surface of the Earth, well displaced from the other interferometers, so that we get a much better sense of where that source is located. That has all sorts of benefits, particularly when we're looking at sources that could also be seen by electromagnetic astronomers. So that's very exciting science. Um, I would say in general, even if, stepping outside of gravitational wave physics, just science in general, I would think a young person who has an interest in that area should definitely pursue it. Um, I mean, to me, it's an exciting thing to do. But even if you don't end up being a scientist, just gaining the knowledge and the technical skills required to understand the science and to make progress in it is going to be helpful to you in a career. Um, we live in a world that is increasingly technological, and having technical skills associated with science, for computer programming, for example, that is obviously beneficial. Um, and so I would say go for it if you like science. Dig into it, learn as much about the particular topics that interest you, but also keep in mind that you want to be well-rounded. So um, learning technical skills such as computer programming along the way is very useful, and learning laboratory skills may be helpful and relevant. Yeah, if you have a passion for science, then that's something to be pursued, I think.
Absolutely, sir. Okay, so thank you so much, sir, for your time today.